Welcome students, welcome to today's session of ALPHORES e-learning program. Let us discuss about the applications of expansions of solids. In the previous class, we have studied about the pendulum clocks, how the pendulum clocks will be giving a time which is not correct as per the changes of temperature. As we have explained in the previous class, at hot summer, because of change in temperature, there will be an increase in the length of the pendulum. As a result, time period will increase and they will be executing less number of oscillations. As the pendulum clock is doing less number of oscillations, automatically the clock also goes slow, or it will lose time. So we said that the pendulum clocks will be going slow during the hot summer or at places of high temperature. And next one, at low temperatures or in cold countries otherwise, then what happens? As the temperature is decreasing, they will be contracting in length. As the length of the pendulum decreases, time period decreases, so in the same amount of time it will be executing more number of oscillations. So that will be going fast. So how these clocks will be changing, giving a time which is not correct, that depends upon the changes in temperature. Now corresponding to that, let us move on to the numerical portion, that is how to determine the change. After that we will go for some numericals also. Suppose for any pendulum, we can say that the relation between the time period or the time you are measuring is, yesterday we have given the relation, it is proportional to L power half. Otherwise, if you take the relative changes delta T by T, it becomes a half of delta L by L. And this delta T by T, what is delta T by T? You are measuring a time, whether it is 1 minute or 1 hour or 1 day, any time what we are measuring is T. And in this time T that we are going to measure, the change or error because of change in temperature is delta T. So let us say delta T by T is half delta L by L, but we know this is half. Delta L is the increase in the length of the pendulum corresponding to a change in temperature. Let us say the change in temperature is delta theta. Delta theta is the change in temperature. Then this delta L we can write as L alpha delta theta divided by L, so that that will be equal to half alpha delta theta. So delta T by T we can measure as per this equation, where delta T, this is the time you are measuring, and delta T is the change in the time or the incorrect reading given by the clock, the error or the difference of the correct time and the time given by that clock at that condition of temperature, that is delta T. So we can say that delta T will be equal to half of T of alpha of delta theta. So here delta theta represents the change in temperature and delta T represents the change in the time or loss of time or gain of time. Because in hot summer we said there will be a loss of time, or in very low temperatures there will be a gain of time. So delta T we can measure from this equation. So delta T will be equal to half of T of alpha delta theta. Here delta T represents the loss or gain of time and delta theta represents the change in temperature. So depending on the change in temperature, we will get this equation, or we will get the value of delta T. Very clearly, the pendulum clocks will be showing correct time only at a particular temperature. More at a temperature higher than that, they lose time. At a temperature lower than that, they will gain time. Now let us have a numeric application here itself. Now let us go for it. We can use this equation to find out the change in the time. Suppose there is a pendulum clock that gains 10 seconds of time, 10 seconds of time in a day at a temperature like 40 degrees centigrade. That means when you are using the pendulum clock at a temperature of 40 degrees centigrade, it is suppose because it gains at low temperature, let us take it as some 10 degrees centigrade, it gains time. That means in one day it will be showing a time 10 seconds more of time. That means it is gaining a time of 10 seconds per day, whereas it is losing 10 seconds per each day at a temperature 50 degrees centigrade. That means practically at the 10 degrees centigrade it is gaining 10 seconds per day, and at 50 degrees centigrade it is losing 10 seconds per day. Then what is the temperature at which it will show the correct reading? Let us find out the temperature at which this pendulum clock will show you the correct reading or correct time. So let us find out now. Suppose theta is the temperature at which it gives the correct time. Let us say theta is the temperature at which it gives the correct time. But at 10 degrees centigrade it is gaining 10 seconds per day. We know that the pendulum clock will gain time only at a temperature smaller than the temperature at which gives the correct time. So very clearly this 10 degrees centigrade is smaller than the temperature theta at which it gives the correct time. And similarly, because it is losing time, this 50 degrees centigrade is greater than the temperature at which it is giving correct time to you. So very clearly, let us consider the equation change in the time delta t equal to half alpha delta theta multiplied by t. T is the same but is 1 day. We are taking a time of 1 day in both the cases. So T is the same. Now both are made up of the same material. Alpha is also the same because we are talking about the same pendulum. So alpha is the same. So very clearly change in the time is proportional to change in the temperature. Change in the time or loss or gain, that is proportional to change in the temperature delta theta. Let us apply now. What is delta t? 10 seconds of time here and again 10 seconds of time also. But this delta t corresponds to what is that? Initially it is gaining 10 seconds. So change in temperature is, it is giving correct time at temperature theta but losing 10 seconds at temperature 10 degrees centigrade. Very clearly the change in temperature is theta minus 10. Let us try to understand this point. Theta is the temperature at which it gives the correct time. But at 10 degrees centigrade, it is gaining 10 seconds of time. That means this 10 degrees centigrade is smaller than the value of theta. So from that theta, the change is theta minus 10. Corresponding to this, again there is a loss of 10 seconds of time correspondingly at 50 degrees centigrade. Very clearly 50 is the temperature which is more than the correct reading temperature. So change in temperature in this case is because it is 50 is more than theta, 50 minus theta is the change. So very clearly because it is gaining 10 seconds and also losing 10 seconds, this ratio will be equal to 1. So very clearly theta minus 10 will be equal to 50 minus theta. Then you can bring this here. 2 theta will be equal to taking to the other side, it is 60 degrees. Otherwise you will have theta equal to 30 degrees centigrade. That means this clock will show you correct time at a temperature 30 degrees centigrade. Taking this theta to the other side, 2 theta becomes 50 plus 10 60, so theta is 30. That means at temperature theta 30 degrees centigrade, it shows the correct time, and because of decrease of temperature 10 degrees, it is gaining the time here, and because this is higher temperature, it is losing 10 seconds of time. So while doing this problem, we have to remember one important point. The temperature at which it is gaining the time, the temperature at which it is losing the time, the temperature at which it will be showing the correct time, all the three, you can say between these two you will have the temperature. That means the temperature at which it gives it gains the time is smaller than the temperature at which it shows the correct time, and the temperature at which it is losing the time, that will be more than the temperature at which it gives the correct time. So our answer will be in between these two. Our answer will be in between these two. But to proceed, we have to apply like this. This is one important a model of numericals related to this point which we have to understand. And sometimes there is another possibility. Let us consider one more numerical here itself. Suppose there is a pendulum clock made up of a material, let us say alpha equal to 5 into 10 power minus 6 per degree centigrade. That is the value of alpha. Now I am taking a pendulum clock which shows correct time at a temperature 10 degrees centigrade. It shows correct time at this temperature. Suppose I am using the clock at a temperature 40 degrees centigrade. I am using the clock at a temperature 40 degrees centigrade, but it will show correct time at a 10 degrees centigrade only. Very clearly we are considering a temperature which is higher than the temperature corresponding to correct time. Very clearly, because you are using at a higher temperature, there will be a loss of time. There will be a loss of time because it is higher temperature. So let us find out the loss of time in a particular time, or let us say in 1 hour of time, what is the loss? For every 1 hour, what is the time lost by the clock? Or you may be asked to find out the loss of time per day, loss of the time per day, or loss of time for 1 hour or 1 minute, anything we can calculate. Because in our equation, delta t is the loss or gain in a time given by, that is half alpha t into delta theta. We are using this time. In this time, this shows the loss or gain. That means suppose you are asked to find out the loss of time or gain of time in 1 day, take the t as 1 day. Or if you want to calculate that loss or gain of time per 1 hour, take this 1 hour. Then you will get error also, or a loss or gain also in 1 hour only. 1 hour only. But also you want when you are solving this problem, we have to check one more point is your answers. Your options, what is the unit given? Suppose we are asked to find out the loss or gain of time in 1 day, and final options are present in seconds. Final option is present in seconds. Then remember that delta t, when the answer is in seconds, you take this time also in seconds. Or if the answer is in hours, take t also in hours. For example, let us use this equation. I want the loss or gain of time, because the temperature is 40, there is a loss of time. Let us find out the loss of time in 1 day. And suppose the answer is in hours, then what happens? So delta t will be equal to half alpha is 5 into 10 power minus 6, and we are going to find out the loss or gain of time in 1 hour, in 1 day, but answer is in hours. So take this time also in hours, that is take the hour time as 24 hours because it is day, and change in temperature is initially it shows correct time at 10 degrees. Now the time we are using at a temperature 40 degrees. So the change in temperature is 40 minus 10, it is 30 degrees centigrade. So if you multiply all these factors, you will get the answers. So because we are measuring the loss of or gain of time in 1 day only, but if the option is in hours, use this time in hours only. Suppose the answer is in seconds, the final option is in seconds. Let us express the time also, that is 1 day, in seconds. Then what will be the answer? That is, let us say delta t will be equal to half alpha 5 into 10 power minus 6. Remember, we are using a time of one day, but because the option is in seconds, the time also we have to express in seconds. So write down the time in 1 day is it is 86,400 seconds. That is the value of t, and delta theta is 30. You will get the answer in seconds. So this is a numerical calculation, mathematical calculation. We can do it. But thing is, verify the option. If the option is in seconds, you can take the time as time also in seconds. Or if the option is in hours, use the time of 1 day in hours. By calculating the final option, you will get the answer. So how to approach the particular problem, that we have to understand. So here alpha is given in the temperature, 10 degrees centigrade is the temperature at which it gives the correct time. But we are asked to find out the loss at 40 degrees centigrade per day. So depending upon the option, if it is in hours, let us substitute the time as 1 day as 24 hours. Or if the answer is in seconds, you use the time 1 day equal to 86,400 seconds. Let us substitute and calculate. So this is also one important application where we can solve the problems. Right. Now let us move on to some more applications of this expansion of solids. Numerical. Let us go ahead with numericals. Already we have done 2 numericals here, and I am taking a material alpha equal to 5 into 10 power minus 6 per degree centigrade. Now how to approach with the problems? Taking this value of alpha, I will try to solve some more number of numericals for your understanding. So try to understand or try to follow carefully. Alpha I have taken as 5 into 10 power minus 6 per degree centigrade. Number 1. Suppose there is a rod of length 10 meter. The rod of length 10 meter. Suppose I have increased the temperature by 100 degrees centigrade. What is the change in the length of the rod? So initial length of the rod is 10 meter and change in temperature is 100 degrees centigrade. Then what is the change in the length of the body? Let us find out. So change in the length, delta L equal to how much? L alpha delta T. Let us substitute the values. This is the equation we know. Change in the length is L alpha delta T. Let us substitute. What is the value of L? 10 meter. Alpha 5 into 10 power minus 6 per degree centigrade, and change in temperature is 100. Then what you will get here? This is 100 into 10, 10 power 3. 10 power 3 is cancelled. 5 into 10 power minus 3 meter. 10 power minus 3 meter is nothing but millimeter. So this becomes 5 millimeter. So the change in the length is 5 millimeter. So directly you can find out. And similarly, let us find out here the percentage change. Percentage change is delta L by L of 100. Or simply it is alpha delta T, because delta L by L is alpha delta T into 100. That is the percentage change. So what is percentage change? Let us calculate here. Substitute here. Alpha is 5 into 10 power minus 6. Delta T, the change in temperature is 100, and again there is a factor 100. So it is 5 into 10 power minus 2. This is the percent. Otherwise it is 0.05%. That is the change in percentage change in the length of the body. So delta L and the percentage change in the length we have calculated. Now let us proceed with some more numericals. Let us have the same value of alpha for convenience. Now let us calculate like this. Suppose there is a metallic a rod of length, let us say 10 meter. Length 10 meter. Now for this rod I am increasing the temperature. When I am increasing the temperature, the length of the rod is increasing by some extent. Then I found that the length of the rod is increased by 0.05% in this problem that we have solved just now. Now I have given this to data. I have taken a rod of length 10 meter whose value of alpha is 5 into 10 power minus 6 per degree centigrade. When the temperature is increased by 100 degrees centigrade, percentage change in the length is 0.05%. Then what is the, by this I have taken a metallic plate. I have taken a metallic plate of dimension, this is 10 meter and this is 5 meter. I have taken a metallic plate of the same metal having the same value of alpha, but the dimensions are 10 meter and 5 meter. Now for this metallic plate which is made up of the same material as the rod, what is the percentage change in area? Percentage change in area, because percentage change in the length is given to you. But body is different. This is a rod. This is a rod where percentage length is 0.05%. But now with the same material, we are using a metallic plate of dimension 10 meter and 5 meter. For this metallic plate, I want to find out percentage change in area. Then how to do it? Percentage change in area. Remember, percentage change in area is delta A by A multiplied by 100. What is delta A by A? It is beta delta T into 100. Beta delta T into 100. But we know for an isotropic solid, we have shown that alpha, beta, gamma will be in the ratio 1:2:3. So this beta I can write like 2 alpha into delta T into 100. But alpha delta T into 100, this is nothing but percentage change in the length that is already given to you. Just multiply with that. 2 into 0.05, that is 0.1%. So if the percentage change in the length is given, just multiply with 2, you will get the percentage change in area of any plate. Remember, whatever will be the length and breadth, we need not worry about that, because percentage change in area will depend only on alpha and change in temperature. When alpha and change in temperature are same, automatically it is percentage change in the area is double the percentage change in length, and percentage change in volume is triple the percentage change in the length. In the same way, suppose there is a cube. There is a cube of the same material and having a side of 20 meter. Suppose it's a very big cube. Let us assume I have taken a cube of dimension 20 meter made of the same substance. For the same change of temperature 100 degrees centigrade, what is the percentage change in the volume? Simply because change in the volume, percentage change in the volume is delta V by V of 100, that is gamma delta T multiplied by 100. And gamma, we know it is 3 alpha delta T by multiplied by 100. So alpha delta T into 100, it is already given to you. It is the percentage change in the length. Multiply with 3, it becomes 0.15%. Directly you will get the result. So if percentage in length, change in the length is given, directly percentage change in area is irrespective of dimensions. When you take any plate but made up of the same substance corresponding to same change of temperature, the percentage change is doubled in area. Percentage change in volume is simply triple that, you will get the answer. So this is also one easy and important application. Now let us move on to another important model problem. Suppose there are two rods. Each of length 10 meter. I have taken two rods. Both are having the same length of 10 meter. But for the first material, this is alpha 1 is 5 into 10 power minus 6. For the second rod, let us say alpha is 8 into 10 power minus 6 per degree centigrade. Both are having the same initial length of 10 meter. Both are having same initial length of 10 meter. Let us say at the temperature some 20 degrees centigrade. At a temperature 20 degrees centigrade. Both are having the same length of 10 meter. But now I have increased the temperature of both the rods up to 100 degrees centigrade. So initial temperature is 100. Let us say this is theta 1 and final temperature is 100. That is final temperature. So what is the change in temperature? From 20 to 100 we have increased the temperature so that the change is 80 degrees centigrade. Now what happens? What we want actually? Both the rods are having the same initial length of 10 meter. But because of this change in temperature, both of them will not expand equally. Why they do not expand? The change in the length or expansion of the length of the rod, delta L is L alpha delta T. L alpha delta T. L is same for both of them. Delta T is also the same for both of them. But alpha is not the same. So because alpha is different, remember that alpha, beta, gamma are the properties of the material. They are made up of two different materials. So alpha is different. So because alpha is different, the expansion will not be the same. Now what we can calculate here? I want the difference in their length. I want the difference in their length at 100 degrees centigrade. Initially at 20 degrees centigrade, they are having the same length. But at 100 degrees centigrade, what is the difference of their length? Let us find out. Suppose the first rod expansion is delta L1, we can write L1 alpha delta t. And for the second rod expansion is delta L2, that is L2 alpha delta t. Now I want the difference of these two, because initially they are having the same length. Now the final length, the difference between them will be equal to difference of their expansions, because initial length is the same. Therefore L2 minus L1, where L2 and L1 are the final lengths, let us suppose, then that is nothing but delta L2 minus delta L1. Now what is this delta L2 delta L1 here? L2 alpha delta t minus L1 alpha delta t. Otherwise simply it is L alpha 1 here and L alpha 2, because initial length is the same. This is delta L2, that is expansion the second one, and this is the expansion the first one. So taking L of delta t as a common factor, it is alpha 2 minus alpha 1. L delta t, L alpha 2 delta t is delta L2 expanding the second rod, and delta L2, let us take this here also, the initial length is the same, alpha is different, right? Let us make a change. Now delta L2 minus L1 is the final difference in their lengths. Then L delta t alpha 2 minus alpha 1. Let us substitute here. The final length is, initial length is 10 meter. Change in temperature 100 minus 20. It is 80 degrees centigrade. Alpha 2 minus alpha 1. 8 into 10 power minus 6 minus of 5 of 10 power minus 6. The difference is 3 into 10 power minus 6. So let us multiply. It is 3 into 8, 24. So 24 multiplied by, there is a 100 factor here, into 10 power minus 4 meter. Otherwise you say 2.4 multiplied by 10 power minus 3 meter. So you can find out the difference of their lengths. You can find out the difference of their lengths at the higher temperature. Right. This is also an important numerical example to you. Now let us move on to another numerical example. Suppose I have taken a scale. I have taken a scale made up of a material whose value of alpha is 5 into 10 power minus 6. I am taking this alpha value so that it is easy for calculation part and easily we can understand. Now alpha is 5 into 10 power minus 6 per degree centigrade. I have taken a scale like this whose length is 1 meter. And it will show the correct reading at a temperature 20 degrees centigrade. We know the metallic scales will give you correct reading or correct length only at a given temperature where it is prepared. At higher temperatures, the length will be more, but it gives a smaller reading. We know how we have calculated how to correct the reading also. Now, what I want is, I want an accuracy. The percentage change or the percentage error in the measurement of the length of the scale, it should not be more than 0.05%. This is the maximum permissible error. This is the maximum permissible error. Error should not be more than this. Error should not be more than this when you are measuring the length using this scale. Then what should be the highest temperature up to which I can use this scale? The scale is prepared at a temperature 20 only. That means at 20 degrees centigrade, it will show you the correct reading. It will show you the correct reading. But what I want is, up to what high temperature I can use this scale for a measurement. But the condition is, the error, percentage error should not be more than 0.05%. That means what is the final temperature up to which you can use? Let us find out. This is the percentage error given. But we know the percentage error delta L by L of 100. What is the equation for this? Delta L by L is alpha delta T multiplied by 100. This is the percentage error. But what is the value given here? 0.05, or it is 5 into 10 power minus 2. Then let us substitute here. What is the value of alpha? 5 into 10 power minus 6. Sorry. Yes, 5 into 10 power minus 6. And delta T, we don't know the change in temperature. So let us say delta T is the change in temperature into 100. That equal to 5 into 10 power minus 2. This is the value of alpha delta T into 100. This is the percentage change. But this percentage change is equal to 5 into 10 power minus 2, because the maximum permissible error or permissible difference with respect to the actual length is only 0.05%. That means any length you measure using the scale, there may be error because of change in temperature. But the condition is error should not be more than this percent. So let us find out percentage change in the error is this much, alpha delta T into 100, but that is given by 5 into 10 power minus 2. Now let us apply. Alpha is 5 into 10 power minus 6, delta T we don't know, and 100 is 100, this is 5 into 10 power minus 2. Let us calculate now. I want the value of delta T, right? Delta T, that equal to 5 into 10 power minus 2 divided by, this is 5 into 10 power minus 6 multiplied by 100. So this becomes 10 power minus 4. Then what you are getting? So 10 power minus 4 comes to numerator, so that becomes 10 square here. Final answer. So delta T is 10 square, that is 100 degrees centigrade. But remember, delta T, change in temperature, maximum possible value, so that the error will not exceed this limit, is 100 degrees centigrade. But I want the temperature. That means suppose you can use the scale up to a high temperature, let us say theta. So theta is the highest temperature, but it shows correct length at 20 degrees centigrade. So with respect to this 20, the change theta minus 20, that must be equal to 100. That means the final temperature up to which you can use the scale, so that error will not cross this limit, that is given by 100 and 20 will come to the side, it is 120 degrees centigrade. That means at 120 degrees centigrade, the error will be 0.05%. That means up to 120 degrees centigrade you can use. So it is prepared at 20, and even if you use at 120 degrees centigrade, the error will not be crossing the maximum limit. So the highest temperature up to which it can be used is 120 degrees centigrade. So this is how we can calculate another important numerical related to this topic. Now let us move on to another case. In one class we have studied about a wooden wheel placed inside an iron tire. Iron tire will be having initially prepared with a smaller radius or diameter. Now if we want to place a wooden wheel in an iron tire of smaller diameter, we said we have to raise the temperature of the iron tire. Now let us have a small application, numerical application with that. I have taken suppose the value of alpha for iron, it is 8 into 10 power minus 6 per degree centigrade. Let us take the value of alpha like this. And now initially the wooden wheel, let us say wooden wheel has a radius of let us say 101 centimeter. 101 centimeter. Wooden wheel has this much of radius. Let us say radius. Radius is 101 centimeter. But I have taken the iron tire or iron wheel. It will be having a radius of 100 centimeter only. 100 centimeter only. But now we have to keep this wooden wheel of radius 101 inside the iron wheel or in iron tire, otherwise 100 centimeter of only 100 centimeter radius. Very clearly we cannot fit this one into this because the radius is more here. Then what we have to do? We have to heat the iron tire so that the radius becomes at least 101. When the radius of the iron tire is exactly 101, wooden wheel can also be placed exactly fitting inside that. So what we have to do? when the wooden wheel is having a radius of 101 centimeter and iron tire or iron wheel is having 100 centimeter, suppose the room temperature is 30 degrees centigrade. Let us say the initial temperature. Now I want to heat this iron wheel until the radius will become 101 centimeter. That means what should be the change in the radius here? From 100 to it has to expand to 101 centimeter. So change in the radius is 1 centimeter. So delta R equal to R alpha delta T. R alpha delta T. So delta R is 1 centimeter and initial radius of the iron tire is 100 centimeter. Alpha we know. Let us find out the temperature up to which it must be heated. And now let us say this R alpha delta T. Suppose it is heated to a final temperature theta, so that initial temperature theta 1, then change in temperature is theta 2 minus theta 1. Theta 1 we know 30 degrees centigrade, and what we are asked to calculate the final temperature up to which it must be heated. Up to what? The final temperature up to which it must be heated, so that the wooden wheel can be placed inside the iron tire. Remember that wooden wheel you can place inside the iron tire, so that it is possible only when their radii are equal. But the radius of the wooden wheel is 101 and radius of the iron tire is only 100. So it should expand by 1 centimeter in the radius. Let us go ahead. So delta R we know it is 1 centimeter and radius is 100 centimeter. Alpha 8 into 10 power minus 6 per degree centigrade. Final temperature theta 2 minus theta 1. So let us say this is theta 2 minus initial temperature is 30. We know this value theta 1. So very clearly theta 2 minus 30, that is change in temperature is given by taking to this side. This becomes 100 into 10 power minus 6, 10 power minus 4. So taking to the other side it becomes, we want this value, right? So 1 by 8 into 10 power minus 4. Otherwise 10 power 4 by 8, that is theta minus 30. 10 power 4 is nothing but 10,000. 10,000 by 8. 10,000 by 8 it is theta 2 minus 30. So let us find out its value. So 10,000 by 80 means it is 1. Here 20, that is 2 times, and again 40 you will have 5 times 50. So 1250 is the change in temperature. Theta 2 minus 30 is 1250 degrees centigrade. But I want the final temperature up to which the iron tire must be heated. So final temperature theta 2 must be equal to 1250. Bring this 30 to the other side. So it becomes 1280 degrees centigrade. So at this temperature theta 2 equal to 1280 degrees centigrade, you will have the radius of this iron tire increasing to 101 centimeter, so that the wooden wheel can be placed exactly fitting into the iron tire. So this is another important numerical application related to this, right? Now let us do one more numerical application. Suppose we have studied about the pendulum clocks, changes in time. We have taken about the length, changes in the length and percentage changes in length, area, etc. And this application is also complete now. Let us move on to one more application. Suppose let us consider an application like this. Suppose as when you are increasing the volume of a body because of change in temperature, there will also be a change in the density also. Then how to calculate the variation of density with temperature? Let us discuss that also, because we are left with a small topic that is, after that we will come back to the one more numerical application. We know that whenever a body of volume V is heated to a change in temperature delta T, the change in the volume is given by delta V equal to V gamma delta T. V gamma delta T, where delta V is the change in volume and gamma is the coefficient of volume expansion, and delta T is the change in temperature. But whenever we are heating a body, there is always an increase in the volume, but mass remains constant. Mass always remains constant. As a result, if you take mass of the body, it is always the product of volume and density. So mass is volume into density. But now at different temperatures for the same body, volumes are different. So as volumes are different, let us say this mass equal to, at a temperature T1 degrees centigrade, volume is V1 and corresponding to that density is D1. So this is at temperature T1 degrees centigrade. For the same body, suppose I am heating at temperature T2 degrees centigrade, where the volume is V2 and the density is D2. Now, because mass of the body is the same, initial mass at temperature T1, V1 D1, and at temperature T2, it is V2 D2. But both of them should be the same because mass will not change. Therefore, let us consider the equation V1 D1 equal to V2 D2, where V1 is the initial temperature, D1 initial density at lower temperature T1 degrees centigrade, and V2 is the final volume. Now let us substitute for the final volume. We have derived an equation for that previously, that is V2 equal to V1 of 1 plus gamma of change in temperature, that is T2 minus T1. This is the value of V2 multiplied by D2. Now I want, this is V1 of D1. So when you cancel the term V1 here, D1 equal to D2 of, D2 is the density at higher temperature. So D2 of 1 plus gamma of T2 minus T1. So here we can find, this is the relation between the densities of the body at temperature T1 degrees centigrade and T2 degrees centigrade. So D1 equal to D2 of 1 plus gamma of T2 minus T1. Now, considering the initial temperature and final temperature, suppose I have taken the initial temperature T1 as 0 degrees centigrade and the corresponding density, let us say D0, and the final temperature T2 I will take as T2 temperature degrees centigrade as some T. T degrees centigrade is the final temperature where the density is D here. So in terms of 1 and 2, I am taking the symbols D0 and D here. Now what will be the values here? D1 is the density at lower temperature. We have to remember that when the temperature is increasing, volume is increasing, but density will decrease to keep the mass as a constant. That's why at lower temperature, density is more. At higher temperature, density is less. So now using this equation, D0 will be equal to D of 1 plus gamma, change in temperature, T minus 0, simply it is T. Otherwise, you will say D equal to D0 by 1 plus gamma T. We can use this equation. Practically, D0 is the density at 0 degrees centigrade and D is the density at T degrees centigrade. So, as far as numericals are concerned, we can calculate the density at a temperature T by using this equation. D equal to D0 by 1 plus gamma T. Practically, this factor to calculate it is difficult. So, what we do? Let us multiply with 1 minus gamma T in the numerator and denominator. Then what you will have? D0 of 1 minus gamma T by, this is 1 plus gamma T multiplied by 1 minus gamma T. It is A plus B of A minus B, A square minus B square. So 1 minus gamma square T square. Now what we have to do with this? Remember, in this equation we have the term gamma square. We know already all these alpha, beta, gamma values are of order of 10 power minus 6. So this will be of 10 power minus 12. So this factor will be very, very small numerically, so that the small factor can be neglected. If we neglect this one, what we will have? D equal to D0 of 1 minus gamma T. So these two relations we can use to solve with the problems. If density at 0 degrees centigrade is given, and if you want the density suppose at 100 degrees centigrade, use this relation D equal to D0 of 1 minus gamma multiplied by 100, you can find out. Otherwise, if D value is given, density at 8 degrees centigrade, you want the density at 0 degrees centigrade, directly you can use this relation, that is D of 1 plus gamma T. So numericals, as far as they are concerned, we can use these two equations to find out how the density is changing. So this is also an important application. Right. Now, With this, I have given some numerical application to understand the topic, and once again go through all those numericals and try to solve as many as number of problems. Right? With this, let us close this class, and we will meet in the next class. Thank you.